Have you ever really stopped to think about the speakers that are all around us? I mean, they're in our phones, our TVs, our cars, just absolutely everywhere. And what they do is, honestly, it's kind of magical. They take this invisible thing, electricity, and they turn it into sound. Sound that can make us feel something, make us dance, tell us a story. It seems so simple on the surface, but the physics behind how it all works, it's fascinating. Okay, so let's just jump right in with something that might blow your mind. This is not science fiction, this is real. The sound waves coming out of a speaker are a literal physical force, a force so powerful and so precise it can make tiny things float in midair and even be used to perform surgery without ever making a cut. That's the kind of power we're talking about, hiding in plain sight in our living rooms. So that really gets us to the heart of the mystery, right? You've got a box, you've got a wire with electricity flowing through it, and somehow, that combination creates these incredibly powerful, complex vibrations in the air. How on earth does that actually happen? Well, that's exactly what we're going to pull apart in this explainer. To figure it all out, we're going to follow the entire journey. First, we'll get into the basic principle. How does that electrical signal become a physical vibration? Then we're going to get our hands dirty, do a little virtual surgery on the most common speaker out there to see how all its parts dance together. And to top it off, we'll look at some other, frankly, pretty wild and exotic designs that took a totally different approach. All right, first things first. Before we can get into all the cool hardware, the cones and the magnets and all that, we have to understand the most fundamental step. We have to grasp how a simple electrical current even begins its transformation into the music and voices that we hear. So, at its most basic level, what even is sound? Well, it's just vibration. That's it. Picture a single particle of air getting a tiny push. It bumps into the particle next to it, which then bumps into the one next to that, and so on, creating this chain reaction, this domino effect. That pulse of energy, that wave of bumping particles, is what our ears pick up and call sound. And the speaker's whole job is just to start that very first push. Okay, so here's the whole process in a nutshell. It all kicks off with an electrical signal from an amplifier. That signal hits something called a crossover, which acts like a traffic cop for sound, telling the high notes to go to one speaker part and the low notes to go to another. Then, the driver, that's the real engine here, turns that electricity into actual movement. That movement starts the domino effect in the air, creating pressure waves, and finally, those waves travel to our ears. See? Simple, right? All right, let's get to the main event. We're going to zoom way in on that third step and really explore the most common type of speaker driver on the entire planet, the dynamic driver. I'd bet money this is the exact technology you have in your home right now. And there's a really good reason it's so popular. The dynamic driver is an absolute workhorse. It can get seriously loud without even breaking a sweat. It can handle everything from the quietest whisper to a massive movie explosion, and it's just plain tough. But what's really cool is how all of its parts work together to pull this off. Let's start with the part you can actually see moving back and forth. The cone, also called the diaphragm. Its only job is to push air. But that's a massive engineering challenge. It has to be incredibly stiff, so it moves in one solid piece, but at the same time, it has to be super lightweight, so it can start and stop thousands of times a second without any lag. If it flexes or bends even a tiny bit, you get this ugly distortion called breakup. And that's why you see designers obsessing over cone materials, using everything from paper to aluminum to even Kevlar. Now, tucked right behind that cone, you've got the voice coil. You can think of this as the electrical motor of the speaker. It's really just a simple coil of wire attached to the cone. But when the audio signal from your amplifier zips through it, it instantly becomes an electromagnet, with a magnetic field that pulses and changes, perfectly in sync with the music. And right here, this is where the real magic happens. That voice coil is sitting right in the middle of a big, powerful permanent magnet. So as the voice coil's magnetic field is flickering on and off and changing polarity, it's constantly getting pushed and pulled by that permanent magnet. It's this incredibly fast push-pull action that moves the voice coil and the cone that's attached to it back and forth to create sound. Generally, the bigger and stronger that permanent magnet is, the more control it has over that movement. Now, you can imagine all this high-speed movement could get chaotic really fast if it's not perfectly controlled, and that's the job of the suspension system. You've got the flexible ring on the outside of the cone called the surround, and then there's this hidden sort of accordion-looking piece inside called the spider. Together, they act like a perfect spring system. They let the cone move forward and back freely, but they always snap it right back to the center, keeping it perfectly aligned. Without them, the sound would just be a distorted mess. And finally, what holds this whole delicate operation together? The basket. It's just a rigid metal frame, but it's way more important than it looks. It provides the structural backbone for everything. In high-end speakers, these are often made from super heavy cast metal to make sure absolutely nothing flexes or vibrates except for the cone itself. You don't want the frame adding its own unwanted noise to the music. But even this brilliant design isn't perfect. If you push it too hard, a couple of things can happen. Ever cranked the volume and heard a really nasty pop or thwack sound from your subwoofer? Well, that's called bottoming out. It means the voice coil moved so far that it literally slammed into the back of the magnet. The other issue is heat. At high volumes, that voice coil gets hot, which increases its electrical resistance, so it actually produces less sound. That's dynamic compression. The loud parts of the music get squashed.
So yeah, the dynamic driver is king of the hill, no doubt about it. But it's not the only way to solve the puzzle of making sound. Some engineers went down a totally different road, and they came up with some truly exotic and often beautiful-sounding alternatives.
And it's really helpful to think about it like this. Every type of speaker is just a different set of choices and compromises. One design might be all about raw power and efficiency. Another might sacrifice that power for incredible speed and detail. There's no single best way to do it, just different engineering solutions for different goals. And this table just lays out those trade-offs perfectly. You've got our good old dynamic driver, the champ of power handling. Then you have planar magnetic speakers, often called ribbons. In these, the voice coil and the diaphragm are the same thing, just a super thin, conductive ribbon. This makes it insanely fast and responsive, but also not very efficient. And then there are electrostatic speakers, which use a totally different principle, static electricity, not magnets, to move an ultra-thin membrane. This gives them incredible transparency and detail, but they have to be plugged into a wall outlet to work. And then there's this really cool, kind of weird one, the air motion transformer, or AMT. Instead of pushing air like a piston, its diaphragm is folded up like an accordion, and when it moves, it squeezes the air out from between the folds. The source material had this amazing analogy for it. It's like gently squeezing a piece of fruit and watching the seeds shoot out at high speed. It's an incredible design that actually moves air 5 times faster than the diaphragm itself is moving. Let's just take another quick look at those electrostatic speakers because they are just so different. First off, no magnets at all. It's all static electricity. The part that moves is a sheet of mylar that's thinner than a human hair. You can literally see through it. Because they need to create a static field, you have to plug them into the wall like a lamp. And if you play them way too loud, electricity can literally arc across the panel, which can damage them. Oh, and one more thing. They shoot sound out of the back as well as the front, which creates this huge, open, and very unique sound in a room. Okay, so coils, cones, static fields. Why does any of this stuff actually matter? Why should you care? Well, because understanding the how completely changes the what you're actually hearing and how much you can appreciate it. This really isn't just a bunch of trivia for engineers. Once you understand the incredible challenges and the clever solutions that are packed into that simple box in your living room, it stops being a piece of furniture. It becomes a marvel of physics. It really gives you a whole new way to experience the music you love. So this is what you walk away with. You get a brand new appreciation for the insane amount of engineering that goes into everyday objects. When you read a review that talks about cone material or a ribbon tweeter, you'll actually know what they mean. You might even start to hear the difference between technologies yourself. And you'll finally understand why some speakers cost so much more than others. It often comes down to the quality of materials and the precision engineering used to solve these exact physical problems. And really, that's the thought I want to leave you with. The next time you put on your favorite song, try to listen a little differently. You won't just hear the melody or the words. You'll hear the physics at play. You'll hear that voice coil vibrating thousands of times a second, the cone pushing the air, and that incredible journey from a simple electrical signal to pure emotion. So, now that you know how it works, will you ever be able to listen the same way again?